So the next thing that we'll talk about is the concept of tensors. So before we talk about tensors in special relativity, it's useful to go back and talk about tensors that we're familiar with, maybe from classical mechanics. So let's talk about the moment of inertia tensor in 3 dimensions, 3 spatial dimensions. Forget about time. Moment of inertia tensor. So the moment of inertia tensor is defined as, suppose you have a distributed mass, and we want to find the moment of inertia about some point. Okay. Then the way we define the moment of inertia is we take a small mass element which is located at some vector x bar, and we sum over each mass element by weighting it by, let's say, its x position in the ith direction. So I goes from 1, 3, and its x position in the j direction. Okay. And this quantity is what we define as the moment of inertia tensor after we sum over all these little mass elements. Okay, so we sum over the entire, all the mass elements of the body. And this quantity defines what is called a moment of inertia tensor. Okay, and this is useful when we compute, for example, the energy of this object when it's rotating about some axis, the rotational energy of the body. Or when we're trying to compute, let's say, the response, the angular acceleration of this body in response to some kind of torque which is applied, which is trying to rotate this object. Now, you can clearly see that the components I, j depend on your choice of axes x, y, and z. Okay, so if I choose a different x, y, and z, so x, y, and z, then I would have to rotate my x coordinates, and therefore I would have to correspondingly transform the moment of inertia tensor. Okay, so we want to know, how does the moment of inertia tensor transform under a change of axes? Okay, or what is the dictionary for transformation of the moment of inertia tensor under rotations? Okay. Now we know how the x is transformed. So x transforms by a rotation operator, a rotation matrix multiplied by x. In index notation, we don't use upper and lowered indices for rotations. Okay, that's only comes in when we talk about space-time transformations. We use, in index notation, we would say that x prime I would be rij x. Okay, this would be the transformed x coordinate, where a typical rotation matrix, let's say a rotation about the z-axis by an angle theta, would look like this. Okay, and so given the rule for how x transforms, we can figure out the rule for how I would transform. So the rule is, if we have iij, which is summation over the mass elements times xi, xj. Now the mass elements don't transform under rotation, so that's important, because we only need to transform the xi's. So under the dictionary, after we make a rotation, we would get the new matrix or the new moment of inertia tensor I prime ij, which would be summation over dm x prime I x prime j. And in index notation, again, we can write this as r I. I'll just use a different index here because j has already been used. So this will give us RIL. So remember, this summation is not over indices. This summation is over masses. Okay, the summation is over mass elements. So RIL XL. So I'm actually going to drop this summation because I don't want you to get confused. So there is a summation over mass elements which we're not going to worry about, and we'll now write the x prime I as RIL XL, and there's an implicit summation over L over here, and then there's RI or RJ K X K. Okay, and there's a summation over K. So if I write this out, I can write summation over K, summation over L, and there was previously a summation over the masses, and I can interchange the order of these summations, okay? And I can do the summation over masses first and then do the summation over the indices K and L. So when I do that, I write this as summation dm. Sorry, write it in this way. So RIL RJK summation over masses XL XK. Now the reason I can take the rotation matrices outside of the summation over masses is that the choice of rotation matrix has to do with the choice of our axes, okay, which has nothing to do with the distribution of the mass itself. Whereas the positions of the mass in one coordinate system certainly do depend on which mass element I'm talking about, so I cannot pull these x's outside the summation. Okay. So now when I do this, I get summation over k, summation over L, RIL, RJK, and this quantity is nothing but our old moment of inertia tensor, which is ILK. So the transformation rule for the matrix or for the moment of inertia tensor I prime looks like this. Okay, if this is in index notation, but we could write this in matrix notation. If we think of I prime as having two indices, I and j, we can think of the matrix I prime as being related to the matrix I by the following transformation. This looks like R dot I dot R transpose. Okay, this is in matrix notation, but this is in index notation. Okay, so you think about the matrix I of the moment of inertia tensor. Imagine hitting it on the right or on the left by a matrix R, and hitting it from the right by a matrix R, but I have to transpose this matrix when I hit it from the right. Okay. Now you could imagine constructing more complicated objects hypothetically. Okay, we don't know what physical quantities they describe, but in principle we could construct something like xi, xj, xk. Okay, so our previous object that we constructed had only two free indices, I and j, so this is called a rank 2 tensor. But something like this is called a rank 3 tensor. Okay, so this is a rank 3 tensor. And we can ask, how does this object transform? And in index notation, again, it's very easy to see how this transforms. So it would be x prime I, x prime j, x prime k, which would be related to the old quantities by ri a, r j b, r k c, x a, x b, x c. Now, this is a more complicated object to look at in anything other than index notation. So if I want to imagine what this object is, I have to think of it as a 3-index object. So unlike a matrix, I have to think of this as a cube of values with, let's say, the index A describing the rows, an index I describing the rows, the index J describing the columns, and k describing the depth. Okay, and this transformation rule is effectively telling me that I have to hit it with a matrix R from the left, a matrix R from the right, and a matrix R in this perpendicular direction. Okay, so it's obviously much more complicated to describe than the simple laws of matrix multiplication that we've written down before, but it's much easier to write down when we write it down in index notation. So this is where the power of index notation comes in. Okay, for rank 3 or higher tensors, it's much easier to write the transformation rules using index notation. Now, you'll see that the way we've constructed this, I runs from 1 through 3, j runs from 1 through 3, and k runs from 1 through 3. So the object that we've constructed has 27 components. Okay, for every independent choice of I, j, and k. So in general, we can write down, and the way we constructed this object, okay, we can write it as a single object with indices I, j, k. Okay, just as we defined the moment of inertia tensor as an object with 2 indices I, j. Now, the way we constructed Ij, or this rank 3 tensor over here, is we took what is called a tensor product, okay, of 3 vectors, or 2 vectors when constructing the moment of inertia tensor. But you can intrinsically assume that there are objects which are not constructed as tensor products, which obey this transformation rule. That is, I don't know what this object is, or I don't know how to construct it from vectors, but I can tell you that the transformation rule for W prime is that it's related to the components of W, the 27 components of W, by some kind of law like this. RIA, RJB, RKC, where there's a summation over ABC. Okay, and similarly, there's a transformation rule for I, which relates it to IAB, that is the old I, okay, RJB. Okay, so this is a dictionary of rotations of a new set of objects which we call tensors. These are rank 2 tensors, and these are rank 3 tensors. And the generalization of this is to construct a rank n tensor, and this would transform in the following way. There would be matrices R Ri1, J1, Rin, Jn, which transform the original W and give us the new W prime. So this gives us the most general dictionary of how different objects can transform under rotations. Okay? And now we just generalize this to special relativity.